So section 5 is the last section of Module 1, and we're going to look at combining everything we've done so far into absolute value inequalities. And when we look at absolute value inequalities, we're first going to focus on the less than or equal to. So only the less than or equal to for the first part of this. And let's start with a little warm-up problem. What values will hold for the inequality the absolute value of x is less than 3? So if we remember our definition of absolute value is how far or the distance we are away from 0. So let me just jot that down as a reminder. The absolute value is the distance from 0. So what this is saying is, if I go back to the inequality, the distance from 0 has to be less than 3. So if I focus on 0, I could go 3 units to the right, and that's going to be less than 3, or I could go 3 units to the left. Anything in between here, if I judge from 0, is going to be less than 3 units away. If I pick 2, it's less than 3 units away from 0. If I pick -1, it's less than 3 units away from 0. So it's any solutions, really, where x is greater than -3 and x has to be less than 3. Now we've talked about writing this as a compound inequality, where we have x in the middle. We know our low point is -3 and our highest point is 3, or as interval notation, -3 to 3. So those would be our solutions here in interval notation to that first warm-up problem. So let's look at generalizing what we just said. If we choose any a, just an arbitrary number, in our previous warm-up example it was 3, what are our solutions going to look like? Well, on a number line, the distance from 0, maybe a is over here, that means -a is down here, needs to be a units away. So anything between -a and a would be our answers. Again, generalizing it, we would say solutions would be anything that's greater than -a, and it has to be less than a. We could write that as a compound inequality. X is between -a and a, or interval notation from -a to a. So thinking about what we had just defined to solve more complex inequalities with absolute value, we know that there are 2 different inequalities that we can form from this one absolute value inequality. If we look back at the previous example, here's what we can say. We know that, whoops, my x is pretty bad there. We know that one solution comes from when x minus 2 is less than 1. We know that the other solution comes from when x minus 2 is greater than -1. That's how we form our 2 inequalities. So essentially what's going to happen in these more complex equations or inequalities is you keep one value or one inequality as the same. The second inequality, you switch the inequality and flip the sign, in this case, to a negative. You switch the inequality and you flip the sign. This is how we form our 2 inequalities. Similar to forming 2 equations when we solve absolute value equations. So I'm going to solve these separately and say, okay, let's add 2. X is less than or equal to 3. And let's solve the other one by adding 2. X is greater than or equal to 1. So our solutions fall when the value is less than or equal to 3, greater than or equal to 1. If I put that on a number line, 0, 1, and 3. So it has to be less than 3, going this way, but also greater than or equal to 1. Include those values. So that means my interval notation would be from 1 to 3. Next example, if I set up two inequalities from this absolute value inequality, I know the first one is going to be 5x plus 2/7 is less than or equal to -4. And then on our second one, remember, we take what's inside, you flip the inequality, and flip the sign to, in this case, a positive. So again, this gets flipped, and this gets a sign change of a flip. Now we need to solve each individually. Well, I'm going to start by subtracting 2/7 from both sides. Let me just do this off to the side. We have a little bit of subtracting fractions work to do. So if I say -4 minus 2/7, well, I need to put this 4 over 1 and try to find a common denominator between 1 and 7. Well, that's going to be 7, so that means I'm going to multiply the first fraction by 7 over 7. So the first fraction, multiply these two together, you get -28. You multiply 7 and 1, 7. Now we have a common denominator. -28 minus 2 is -37. So I'm going to put that back into our inequality that we've been solving. 5x is less than or equal to -37. And now we're almost done here. Let's divide by 5 from both sides. If I divide this by 5 and then divide this by 5, well, just the denominator gets divided. So it's x is less than or equal to -30 over 35. This can simplify down just a bit more. If I take a 5 out of each, -6/7. So here's our first inequality. I'm going to zoom back in. Let's solve this next one. This time I'm going to subtract 2/7. Very similar type of problem. So I'm going to go back, erase what I had up here, and do that similar work for adding those two fractions. We need a common denominator still. There we go. So I have 4 over 1 minus 2/7. Common denominator is still 7, so that first fraction needs multiplied by 7 over 7. We'll multiply across the top. You get your 28 across the bottom. 7ths minus 2/7. 28 minus 2, 26/7. Let's go ahead and divide both sides by 5. So you get x is greater than or equal to 26/35. So if we think about this, it might help to visualize it on a number line. Here's 0. -6/7 would be down here. That's about -0.85. -0.85, if you want to think of it that way. 26/35 is about 0.74, so that would be right up here. And if we think about where our solutions lie on the number line, well, it has to be less than the -6/7, or it can be equal to. And it has to be greater than this. Well, you notice there's no overlapping regions. They split off. like an or inequality. So what that means is there is, and I'm going to write it off to the side, no solution. No solution. Because it has to be less than or equal to a negative and greater than or equal to a positive. That's impossible. No solution. So now let's look at the other type, the greater than or greater than or equal to. And we have another warm-up for these types of problems. The absolute value of x is now greater than 3. What values will hold for the inequality? Now remember, the absolute value is the distance from 0. So what this is saying is, where on this number line will x's have a further distance from 0 than 3? So what that means is, if I look at 3, anything to the right will have a further distance than 3. For example, if I pick 5, 5 has 1, 2, 3, 4, 5 units away from 3, or from 0. That's obviously greater than 3. Also, this applies for the negatives. I want any numbers that have a distance larger than 3 away from 0, so anything left of that negative 3 will work. Writing that as an inequality, well, x can be less than negative 3, or x can be greater than 3. This is now an or statement. When you have greater than or equal to, it's always an or statement. Well, if I look at what that's going to be for interval notation, remember with or statements, we have to use that u in the middle. We're going to say from negative infinity to negative 3, union 3 to infinity. So if you need to write this down, when we have less than or equal to, it's an and statement, like those ones we've done above. We just looked at greater than or equal to is going to be an or statement. That's very nice to have in your notes for the assignment and for the test coming up later. So anyways, let's generalize this just like we did before. If we have any value, the absolute value of x is greater than a, we're going to say, okay, here's your number line, 0, positive a, and negative a. We know that it has to be greater than a or less than negative a. So that means here's your inequality, and very similar to the interval notation above, from negative infinity to negative a, union a to infinity. So applying this again to slightly more complex absolute value inequalities, let's go ahead and set up two inequalities, from x plus 2, absolute value is greater than 4. Just like before, our first comes from the question. Our second, we need to flip the inequality, flip the sign. Not a very good 4. Let me try that again. So you notice the same rules apply. Flip the inequality and flip the sign. So, reminder, this is now an or statement because it's greater than. We have subtracting 2, x is greater than 2, or subtracting 2, x is less than negative 6. And that looks like, well, greater than 2 is anything to the right, less than negative 6, anything to the left. That is an or statement, so that is perfectly okay for what we have. And we can write this in interval notation as negative infinity to negative 6, union 2 to infinity. Again, for our next problem, we have a greater than, so we need an or split inequality. Our first one, 5 times the quantity x plus 3, over 2 is greater than negative 2, or our second one, 5 times the quantity x plus 3 over 2 is less than positive 2. So let's solve this first one. Well, we need to distribute the 5x plus 15 over 2 is greater than negative 2. I will multiply both sides by 2. These 2's cancel. Continue working here, subtract 15. 5x is greater than negative 19, and divide by 5. So our first value is x is greater than negative 19 fifths. Here's our first one. Same steps here to solve. I'm going to distribute first. Multiply by 2. 2's cancel. Subtract the 15. Divide by 5. You get x is less than negative 11 fifths. Graphing this on a number line, I'm going to put it in the space I have right here. This is 0, negative 19 fifths, or negative 3.8 would be right here. I'm going to use the decimal value. Negative 11 fifths, or negative 2.2 would be right here. Now it's greater than negative 3.8. It's less than negative 2.2. And what we notice here is that every solution on this, or every number on this number line, is a solution in this set. The overlap is okay, and you notice everything else is covered. If I plug in any number, it's going to work in my original absolute value inequality. So what that means, since I have everything involved, is I can just write this as, let me put it in green, negative infinity to infinity. Or you can say all real numbers. That means any number I choose will work in my question I was given. And for our last example, we have a little bit of work to do before we set up two inequalities. Because the absolute value is not by itself, as always, we're going to get it by itself first, subtracting 11. The absolute value of x plus 1 is greater than or equal to 8. Let me complete the absolute value on that side as well. Now, set up the two different inequalities. X plus 1 is greater than or equal to 8. X plus 1 is less than or equal to negative 8. Subtract 1. Subtract 1. Let's look at the number line before we write this as an inequality. Remember, because it's greater than or equal to, this is an or inequality. One or the other works. If this is 0, 7's here, negative 9 is down here. So x is greater than or equal to 7. That means anything 7 or above works in our original inequality. Anything less than or equal to negative 9 will also work. My interval notation from negative infinity to negative 9, I'm going to include that because it's less than or equal to union 7, and I'm actually going to include 7 as well. So let's put a square bracket to infinity. So again, combining everything we've done so far in this module, using all those skills to do these absolute value inequalities.